Welcome to lecture 22. In this lecture, I will talk about Schwarzschild solutions. Recall that in the last 4 lectures, we spent quite some time deriving the Einstein field equations. The Einstein field equations are a set of coupled nonlinear partial differential equations that compactly can be written in this following form, where R mu is the Ricci tensor, R is the Ricci scalar, G mu is the metric tensor, T mu is the energy momentum tensor, lambda is a constant, and 8 pi g is 8 pi times Newton's constant g. We found that in the last lecture that the Einstein equations as given in equation 22.1 correspond to Newton's law of gravity if we approximate these equations in a limit where the field is weak, so g mu is very close to Minkowski space, and where all speeds are non-relativistic. In this lecture now, we want to explore the consequence of the Einstein field equations outside of the Newtonian limit, so meaning for looking for deviations for Newton's law of gravity. Since they constitute a set of nonlinear PDEs for the metric g mu with a source t mu, these Einstein field equations are generally hard to solve. We can simplify our task by making some simplifying assumptions, such as trying to solve the field equations first for empty space. Empty space just means that we set the energy momentum tensor T mu to 0, which means that we are studying no matter at all, just pure gravity. So for empty space, then the Einstein field equations are just this: R mu minus 1/2 G mu R plus lambda G mu is equal to 0. We want to make some further assumptions, namely in the following, I will assume that the cosmological constant lambda, which is called the cosmological constant, is set to 0. This is just for the moment a sort of assumption to make the equation simpler. It will turn out that later on, this is actually a good approximation for the goal that we have in mind for this solution, but at the moment it is an ad hoc assumption. So if we make this assumption, then for empty space and for vanishing cosmological constant, the Einstein equation just become R mu minus 1/2 G mu R is 0. We can take the trace of the field equations, which just means that we contract the field equations with the metric tensor G mu. And if we do so, we recognize here the contraction of the Ricci tensor, which just gives us back the Ricci scalar. And here we have the contraction of the metric itself, which just gives us the number of space-time dimensions that we consider. So the first term just comes down to being R. And since we have 4 space-time dimensions, 4 over 2 is 2. So we have R minus 2R is equal to 0. Or R is equal to 0. So for empty space and vanishing cosmological constant, R is 0, and if we plug this back into the Einstein field equations, we find that the Einstein field equations simply become R mu is equal to 0. So now we want to solve the set of partial differential equations that are given by equation 22.7. Turns out that Ricci tensor vanishing is still a set of complicated nonlinear PDEs. We can simplify our task further by demanding additional symmetries of the solutions. One symmetry that we can demand is that we are looking for static solutions, meaning solutions that are independent of time. This means that we can make the ansatz that our metric tensor G mu is equal to a metric tensor that only depends on the space coordinates x, but not on time. In addition, we can further make assumptions about the solutions. And another set of assumptions that we can make is that the solutions we're looking for are spherically symmetric, meaning that the metric tensor G mu only depends on the absolute value of the coordinate x rather than all the coordinates x, y, and z separately. If we want to talk about spherically symmetric problems, it is usually useful to consider spherical coordinates r, theta, and phi. So if we use the spherical coordinates, we can just remind ourselves how familiar quantities look in terms of those coordinates. In particular, we can write down the Minkowski metric, which is just flat space-time in spherical coordinates. We do a usual coordinate transformation, and we find that the metric tensor, the Minkowski metric tensor in spherical coordinates is a diagonal matrix, has a -1 in the time-like component, a 1 in the radial component, r squared in the component that goes along with the angle theta, and r squared sine theta in the direction that goes along with the coordinate phi. So from the metric tensor, we can also write down the line element dr squared. So sometimes it's easier to write down the line element if, in particular, we have a metric tensor that has many components vanishing, such as this diagonal matrix, where all the components except along the diagonal are 0, then it's easier to write down the line element. So if we look at this line element here, which is just the contraction of the metric tensor together with the differential of the coordinates for the metric tensor given by this diagonal matrix here, the Minkowski line element in spherical coordinates is just this. It's minus dt squared plus dr squared plus r squared d omega squared, where the omega squared is just the solid angle interval squared. So it's d theta squared plus sine theta squared d phi squared. And there's a 2 that should not be there. So if we look at this line element here, and that's the line element for Minkowski space in spherical coordinates, what we now want to do is we want to make an ansatz for either the metric tensor or the line element for some other manifold that could be non-Minkowski that still has these properties. It's static and it's spherically symmetric. So what we want to do is we want to modify the form that the Minkowski line element has, and we modify it in the following way. We keep the angular part, the solid angle part, we keep the same, but we allow ourselves for two functions a and b, multiplying the time-like part and the radial part. These functions, if we are interested in a problem that is both time-independent and radially symmetric, can only depend on the coordinate r, but cannot depend on the coordinates t, theta, or phi. So that is our ansatz. And in the following, we want to explore whether such an ansatz can be used to solve the Einstein field equations. Writing it out explicitly, this is the metric tensor for, this is the form of the metric tensor for our ansatz. It is diagonal, has these two unknown functions a and b, and the solid angle part is the same as for Minkowski space. So using this ansatz for the metric tensor, we can now plug this into the field equations r mu is 0 and see if we find a solution for some choices of these two functions a and b. To do this, we need the Ricci tensor for this particular metric. This is some work to do by sort of pen and paper. So we use our computer program to calculate r mu for a metric tensor of this form. I will attach the Mathematica file to the course webpage. And if we do this, then we find that we get an explicit form for r mu such that the combination r0, 0 plus r bar 1 suitably multiplying by functions b and a have a simple form, namely they are just given by ba prime plus ab prime over r times b. Now, since the Einstein field equations say that r mu is equal to 0, this term and this term both vanish. So we find that this combinations of the functions a and b is also vanishing. And by the way, the prime here just denotes derivation with respect to the argument r in this case. Okay, so we find that we have this one equation that these functions a and b have to fulfill if these parts of the Einstein field equations are supposed to be solved. And in addition, we have two more Einstein field equations, R22 and R33, which are not trivially 0. And they give rise to the same equation. The equation for A and B is listed down here. And I think there's a prime missing here. And this equation is something that we also have to make sure is fulfilled if we want to claim to have a solution of the Einstein field equations. So we find that if we use these ansatz for the Einstein field equations, let me back up here, then if B is not equal to 0, then this combination BA prime plus AB prime has to be equal to 0 in order for A and B to be a solution of the Einstein field equations. And that means we want to solve this equation here. Fortunately, this is easy to solve. We find that we can write a solution where we write B as just 1 over A. This is a solution of this equation. And if we plug this back into the other set of Einstein field equations, we find that we have a single ordinary differential equation for A that A has to fulfill in order for the metric ansatz to work as a solution for the Einstein field equations. This equation is simple to solve. We find that it has the solution A of R is 1 plus a constant divided by R. And if we use this solution together with B is 1 over A in our ansatz for the metric, we can verify explicitly that the resulting Ricci tensor is identically 0 for all components. So this is an explicit solution to Einstein field equations. It was first found or published by Carl Schwarzschild in 1915. I just wanted to point out that it's Schwarzschild and not Schwarzschild or any other funny version of his name. It's because Schild is just shield in German and doesn't have anything to do with children. Schwarzschild found or published this paper the same year that Einstein actually wrote down his equations for general relativity. As another bit of trivia, note that he wrote this paper during World War I, 1915, while fighting on the Russian front. And he didn't really sort of see the impact that his work had on general relativity, because it happens that he died 1 year later, also during World War I. So in the next lecture, we want to explore consequences of the Schwarzschild solution, because there's some nice physics that goes along with it. And this concludes the present lecture.